This presentation is adapted from a corporate seminar we give called Packets and Photons, the Emerging Two-Layer Network. And it's a presentation that I've given before and a few other presenters in the companies have given to sort of take a look at where we believe networking is going. And it's not meant to be a definitive authority of saying that things will end up in this certain place, but it's an interesting perspective to see where we've gone so far in networking and where we believe it's happening, and how there's going to be a bifurcation of two fundamental layers in the network, an IP sort of service layer and a transport layer at the optical side, and how these layers are going to interwork together. I have about 50 some odd slides in this presentation, and it'll probably take us about an hour and 15 minutes. I don't expect it to go the full hour and a half, but we'll see. These slides are actually on the NANOG website as well. So they're posted, if you just sort of go down under the agenda, you'll see them. We'll look at a history of IP backbones. It won't be a long history. I know everyone's familiar with what IP backbones look like today, and sort of the emergence of what we call the two-layer network, and sort of what different types of network platforms will do from an IP services standpoint and from a transport optical network layering standpoint, and then what's happening a little bit in the standards and forums, and then we'll talk about GMPLS, or Generalized Multi-Protocol Label Switching. Feel free to ask questions. I can't promise I can answer them since I'm pitch hitting at the last minute, but I will do my best, and I have brought a couple technical resources with me just in case I get stumped. In the late 1980s, 1990s, I think most of us sort of understand how these networks have evolved to date. We have taken our data type networks, our IP networks, and we have piggybacked them over traditional voice TDM transport networks. Those are the bigger networks we're built with sonnet rings, add-drop multiplexers, DACs, ATM switches, and we've been building over time IP networks on top of that. And that has done well for the most part for a while, but it hasn't necessarily evolved to where we need it to evolve to as we see IP emerging as one of the primary driving applications in the internet. So the question is, why do we have so many layers? Well, a couple reasons why we have so many layers is they do different functions, and those functions have evolved over time. So if we look at it from a general standpoint, what each component does, a router is doing packet switching. It's looking at IP headers. Okay? It's doing statistical multiplexing as well. And it can do any-to-any port connectivity and any-to-any connectivity over an entire network as well. Okay? And we can also do some restoration now, both at the IP layer and also at the MPLS layer. ATM and frame relay switches traditionally were great at hardware forwarding. Okay? In the early days, you could do an OC3 and OC12 forwarding lookups in ATM hardware, but you couldn't do them in IP routers. That's changed. I think we all know that's changed since then. You can also do restoration with soft PVCs converting over to backup paths and rerouting very quickly. Mux has allowed us to do some speed mismatching, and we'll see how this has changed, or the need for this is becoming less and less as the demand for bandwidth is becoming greater and greater, and routers can can satisfy that demand. And then your sonnet architecture has done the traditional time division multiplexing to allow us to have different time division channels in the network to support these different applications such as voice, video circuits, IP data circuits, ATM circuits, etc. And we have great restoration sitting inside that layer as well, layer 1. And then we've seen in the last few years the emergence of DWDM, dense wave division multiplexing, now to put more and more raw bandwidth into the network, especially as we're trying to turn up more fibers across the country and across the world. Now, what we've seen is that over time, the vendors have to do more and more integration, and vendors have got a little better at doing this, especially through all the standardization bodies. But some of the problems we also have is you have to have integration of multiple network management systems, which at times don't always work well, so you have to do a lot of manual integration of the networks. And as we have lots of different types of equipment and lots of different layers in the network, there's an increase for capital as well as operational cost. And operational cost, as we all know, is very hard to quantify, but I think we all understand that if you have various functional groups, different functional groups operating a network, the costs are going to be higher and higher. So where have we seen IP backbones evolve to a little bit so far? We've seen the muxes become a little bit redundant as trunk bandwidth has increased. So as the core of the network has gone from OC12 to OC48 to OC192, and routers can now process IP packets at line rate, it's not necessary that we have a mux that can groom up an OC3 or an OC12 port and put it onto a higher speed port such as an OC192. Okay? So now what we've seen is sort of a reduction of one of the components in the infrastructure, meaning the MUX. We've also seen this happen at the ATM layer as well. Early on, we had a lot of vendors out there, a lot of carriers building multi-layer networks where I build a SONET infrastructure, I put an ATM network across the top of that, and then I put an IP network around that. And we'll show some pictures of this a little bit later. As we now have the capability to process packets at OC 192 speeds, and we have some of the capabilities that ATM switches were originally doing for creating soft PVCs and the restoration of those, we don't necessarily need this layer anymore. So now we see next generation IP networks being built with just one layer of IP MPLS and removing that ATM layer or just bypassing that altogether. So the point here is we've actually seen some of these networks go, some of the layers kind of go away, but I think we'll see later that the functionality doesn't always disappear, it just sort of migrates into different components in the network. And one of the questions you have to ask is, well, why do we remove ATM? In the case of ATM, it was great for setting up soft PVCs between two endpoint routers. Okay, but we managed to remove that and put that into the MPLS infrastructure. But some of the problems with ATM is we all know about the cell tax problem. And you got three components of cell tax. You've got your 5-byte overhead, you've got your AL5 SAR, AL5 header information or trailer information, as well as you get imperfect packing. So if you're sending a ping packet, which is 64 bytes, you got to use not two cells. It's a lot of additional overhead. So your range of overhead is between 11 and 20% on average. So why are we paying that penalty when we're not really using the benefits of ATM, meaning all the very fine-grained queuing that's sitting inside of variable bit rate, non-real-time, real-time, and constraint-based constant bit rate, excuse me. One of the next things about ATM originally too was to be able to do a lot of virtual circuits inside an individual port and across the ATM switch fabric. And we've been able to now take that same capability and put it into routers. So we don't necessarily need this infrastructure anymore. So I want to take a look at where things are sort of where things are migrating towards and where we think things will end up in the next 5 years or so. And that is, we believe the infrastructures are going to sort of a two-layer into two different components, two different layers here. There's going to be an IP services layer with IP routers and MPLS infrastructure routers, and there's going to be a transport optical layer. And there's a variety of equipment that's going to sit at that layer, at that infrastructure. And we're seeing this migration. It's not going to happen overnight. It'll happen over time. And the IP routing layer will be used for things like creating services. Okay? For instance, creating VPN layer 2 and layer 3 type services. Being able to do the statistical multiplexing at the edge and grooming up all that traffic to transport across the core. Okay? Providing any-to-any connectivity. One of the reasons that I think that ATM never caught on as sort of as a pan world infrastructure is its inability to do any-to-any connectivity on a global scale and to actually scale to that nature. And what I mean by that is, if you remember back in the early 1990s, IBM was going to make a 25 megabit NIC, ATM NIC, to put in your PC or some workstation, and we're all going to have the ability to set up a switch PVC to anywhere else in the world. Well, I think that didn't happen because when you start to create connections through all the different networking equipment around the world, you have a lot of state to keep at each one of those equipments, each one of the pieces of equipment, and that's too much state. In IP, you keep the state at the endpoints. Okay, and you let TCP figure out how to reroute around how to keep that connection up, and you let the lower level protocols be able to figure out how to reroute those packets if they need to. So I think that's one of the reasons it didn't scale. It's the same reason why RSCP in services didn't scale either. Okay, and we'll see how we use RSCP in a different capacity later with MPLS. So you've got an IP layer, and you also have sitting below it an IP transport layer. An optical transport layer. And inside the optical transport layer, we're going to be using a lot of the infrastructure built to date, such as the TDM standardized framing formats, the ability to do restoration now at the tens of milliseconds, and we can actually do some restoration at the IP layer as well with MPLS in the tens or the high tens of milliseconds. It has great survivability, it's a great use of bandwidth. In effect, especially as you start getting to DWDM, when you can actually take a single fiber and you can run 40 different wavelengths over it. That's a fantastic capability here. So what we need to do is leverage the strengths of one layer and leverage the strengths of the other layer, and over time we need to make them work a little more effectively together. So we'll see, I think over time, and we're starting to see it right now, as these two layers come on board, the data layer and the transport layer. And hopefully, if it's done right, we'll see reduced cost. We'll see reduced complexity as well. I think in the shorter term, we're going to have some more complexity as we start to migrate these networks, and as the equipment vendors from all different aspects, the data and the transport layer, have to work together to figure out how to make these things work together. But if we can make them work together, then we can have uniform administration, operations, and maintenance, which would be fantastic for everybody, even though, again, I believe that we're going to be a ways away. And when we look at signaling, one of the things that's going to be important is to be able to signal from the IP layer through the optical layer. And we've already got good examples now of how to do this with RSVP and LDP and constrained routing LDP. Okay. Not sure why this agenda slide keeps coming up here. Let's take a quick look at SONET and SDH and what it's been able to do for us so far. First of all, it's been able to set up there's very good standards in SONET, and the standards are more or less applicable to the operation side, but also the framing format side. So we can take two OC3s and point them together and pass packets. Okay? But we don't necessarily have all the control plane standardization we'd like to have between different equipment vendors. We also have great restoration. So as we're building these SONET rings, bidirectional rings, and unidirectional rings, we have the ability to now, if we have a problem on one ring and we have a cut, we can actually reroute traffic. It costs us twice as much bandwidth capacity since we have to run these bidirectional rings, but we can reroute very quickly in the tens of milliseconds, especially as we start to enable things like automatic protection switching. Okay? SONET is also great because it allows us to build transparent networks where we can run a voice application over, which we've been traditionally doing until now, and we can run the data applications, we can run the voice applications, and it's a pan transport layer that supports a lot of upper layer infrastructure. So the challenge we have is to remove some of the complexity and some of the interoperability problems and keep a lot of the benefits. So some limitations we have is it was originally engineered for voice. Okay? So one thing to think about is why can't I run just a 5.5 gigabit channel? Okay? So it's groomed up in certain capacities from OC1s to OC3s, OC12s, OC48s, etc. And it's a great hierarchy, but why is it structured so stiffly? And we don't always want to have that structure in the IP infrastructure because we might want to have a 5.5 gigabit channel. And I was talking to someone recently who said that one of the reasons it was done was just for simplicity of the chipset in the SONET equipment, that if they built it that way, they could manufacture chipsets very effectively and cost effectively and inexpensively and with high quality. So it's an interesting legacy aspect that's been sitting around. We have a lot of good interfaces at the framing layer, but not necessarily at the control plane layer. So a lot of networks are built on one vendor's equipment, okay? Because there's a proprietary control plane that's sitting between it. I think IP in routing has taken a little bit ahead of that in the sense that we have interoperability between different vendors' equipment at a control plane layer. So we need to sort of bring that now to the optical world. And the other problem we have is that there's no visibility if you're on the packet side, if you're an ATM switch or an IP router, into what's happening in the optical domain. You don't understand any of that topology. The optical domain to a router is just a clear pipe. From San Francisco to New York, I may have an MPLS LSP, and it may go over a variety of different DACs, ADMs, SONET equipment, and DWDM equipment, and we have no idea. There's a whole different group that organizes that and controls that and brings that up and running. Okay. So I want to take a look at trying to define what is a router and what's sort of at the optical side that sits underneath the router. And it's important because if we start looking at the concept that some people start talking about an optical router and what does that mean and is it really possible, it's important to define what a real router is. The minimum capabilities for routers, it has to be able to forward packets looking at layer 3 inside the ISO 7-layer model. Okay? We've got to be able to pick out all the IP source, IP destination information, source port and destination port information, and be able to forward from any port coming into the box out another port, and to not actually to be able to do that at wire speed as well. So We also need to have inside of that enough buffering to do what we call delayed bandwidth buffering, so that we don't prematurely degrade service and actually drop packets. So we have enough delayed bandwidth to actually make a round trip, to make the packet support a round trip session around the United States, or around certain geographical distances in the world. The other thing we need is internet scale. We need to have protocols for ISIS, BGP, OSPF, MPLS, RSVP, LDP to actually be able to scale to the demands of the internet, which we know are changing all the time. And in some senses, the internet is a giant classroom. You need to have the capabilities to do this, but you need to be able to learn very quickly when you're making these protocols and be able to adapt to the changes in the environment, both from a minute scale, what's happening currently in the network, but also as an organization to develop protocols that will actually scale to the demands, especially as you look at things like what happened on September 4th. And I think the internet is an interesting testament to how well things did reroute, and we didn't see a lot of global problems with the internet by any means, just very localized problems, which is a testament to distributed network. So today's benchmarks are you have to be able to build packet processing technology that can take 40-byte packets and move them from any port in the router to another port in the router, and be able to do that at full line rate, whatever rate you're currently supporting, which currently next generation routers are supporting about 100 OC 192 or 10 gigabits per second doing this. You need to be able to do this independent of load. You need to be able to do advanced lookups for classification and for wire rate filtering, and you need to be able to do this, you need to have characteristics such as class of service, as well as red and weighted red shaping and policing. From a routing standpoint, you need to be able to optimize your routes. You need to be able to make it very simple as well, so that you can actually keep the routing protocol overhead simple in the router, so that you don't actually use up all your CPU cycles to when you're actually in a state of congestion, as well as in a state of rerouting. And you need to be able to do this in a very stable fashion and be able to converge very quickly. I suspect most of this is fairly well known. What's interesting, and I think one of the things that IP routers are sort of migrating towards, is the ability to now offer next generation services on the platform. And if you think of what a lot of carriers did in the 90s, is they built layer 2 VPN services off of frame relay and ATM type infrastructure. And a lot of these carriers are trying to figure out now, what do I do with this infrastructure, and how do I offer a similar type of service to my customer, which was very profitable. And they don't necessarily want to do it on that old architecture. They want to do it on next generation architecture. So we see as routers now migrating to the role of being able to offer services. So you need to have the granularity in a router to look at the different types of packets coming in, especially when you look at the different granularity between HTML packet or an FTL packet, or am I offering a multi-service application? Am I doing voice, video, and IP datagrams off of the same physical pipe coming from the customer into the router? And am I doing things like multicast? So we're seeing routers actually taking on the next generation service capabilities to offer things like multicast and MPLS layer 2 and layer VPNs. So now if we bridge over to the optical domain, people are asking, there's a couple different components that are sitting there inside the optical domain. One is an optical cross-connect. There's two types. There's an electrical optical cross-connect, which means that I'm actually taking an optical feed into this cross-connect, then I'm going to convert it into electrons. I'm going to do some processing on it, and I'm going to convert it back out to optical. So I may be taking in an OC3 ATM interface, converting it now to electrical, and then going back out to a different port with an ATM interface as well. Okay. So the important thing is we're actually converting to electrons, and this technology has been around for a while. What we've seen come online in the last few years are all optical cross-connects. So no electrical components inside of it. So we're not converting, I shouldn't say no electrical components, we're not converting optical packets to electrons and then back out again. So what this is used for, in many cases, is the ability to take different lambdas or different light forms into the router off of one port, keeping them in their waveform, and then migrating them out to another port. And so we need to go from any port to any other port inside of this optical cross-connect. So what is an optical cross-connect? What it allows us to do is connect one port with a lambda to another port. It doesn't necessarily allow us to look inside of that lambda to see all the different packets or the IP packets or ATM cells or SONET framing. Okay? We need to be able to add and drop different lambdas. We ought to bring a lambda in, drop it, or switch it off to another circuit. Typically, this is done at very, very high bandwidth, at OC48 and OC192 speeds. And we need to be able to provision this bandwidth as well inside of these capabilities. It's all done more or less at that layer 1 physical layer. A couple of different types of technology being used in this, and I am by no means an expert in this. One is called MEMS, microelectrical mechanical systems. And what allows us to do is actually, off of one port, bring in a lambda, bring in a light form, and actually bounce it off a tilting mirror. And these mirrors are actually controlled by little motors that are sitting in the silicon substrate. And they can angle the mirror, and they can bounce it off a reflector, bring it back into another mirror, another MEMS mirror, and then back out another port. This is pretty neat technology, but again, what's important is that you're actually only taking a whole lambda when you do this. Currently, the matrices that do these are about 8 by 8 matrices. Okay, so they're not incredibly dense right now, the number of ports that they offer. But the long-term goal is to sort of get to a 1024 optical cross-connect, 1024 ports coming into the switch. And one of the issues that you'll see inside of MEMS and a lot of the other technology is that the switching speed is relatively slow. It's on the order of 10 to 25 milliseconds, as compared to a router, which is looking at an IP packet, and it's doing switching in the nanoseconds range. Okay? So what these tend to be better for is to actually establish a connection from one port to another for lambda, and bulk switching all the information off that light in one port out to another, and keeping that connection up. They're not necessarily meant for being able to switch very quickly. Another type of technology being used is liquid crystal light valves, which is the same technology basically that's inside of your LCD displays. And what it allows you to do is take a light wave in and put it through a polarizing beam splitter, and you actually split it in two halves. And you actually take one half and run it through a liquid crystal cell, and you can actually turn it on or off. And as you realign those waves through another polarizing beam splitter, you can switch the actual lambda form to different ports. Okay. Again, the problem with this is it's done at this sort of millisecond, sub-millisecond ranges, but it's not done in the low nanosecond ranges, which you're used to in sort of routers. As well as, again, the granularity is looking just at the pure lambda. Another technology is actually invented by Agilent, comes from bubble jet printers. Same bubble type technology, and what Agilent ends up doing is actually heating an index matching fluid inside of a silicon substrate to a certain temperature, and then based on how heated it is and the size and the characteristics of that actual bubble, they can actually move the light into a certain direction. The challenge here is to be able to keep that bubble in a consistent state, and Agilent claims that they can continue to keep that for long periods of time. But your switching times are sort of in that 10 millisecond range again. Okay. I don't know if it's actually been deployed in any commercial grade products at the moment. Okay. So one of the things we heard a while back, I forget what the company was, but there was a press release that somebody built an all optical IP router. And I think that they were leveraging terms from the IP domain, which is the IP world, which is very hot technology, and the optical technology, which is again a very hot area, and saying we have an optical router. Okay? And they're really saying we have an optical transport switching device, like an OO device. Okay? But as you sort of look at, the concept of taking in a whole lambda and not converting it to electrons, but saying we're going to take this whole lambda in and try to read an IP header inside of that, or an MPLS header, and switch it out. There's some definite challenges to doing this. Okay? One approach that they're working on in the labs is what's called the pipeline approach, where you split the waveform in half, okay? And you actually take one half of it and you convert it to electrical, and you look at the IP, so one is you convert to electrical, but another one is you actually look inside this waveform at the IP information, and then you send a signal to how the other side of the waveform should actually be switched. And I believe they've done some of this in the lab, but it's a little difficult, and it's very slow at the moment, again, compared to IP routers. Some of the challenges there is that in the routing world, we're used to buffering packets. Okay? Well, how do you buffer light? Okay? One thought is you actually can sort of, fix a photon in sort of an orbit and kind of keep it there for a certain period of time. So I personally think we're a long, long way from being able to have an all-optical router that can do this. Okay. If we go back to this concept of a two-layer network, okay, and we believe that we sort of have an infrastructure of IP, MPLS, packet-oriented devices, and we have another infrastructure of optical devices, whether or not they're OEO devices or OOO devices, meaning pure optical devices. What's going to be interesting to see is how are we going to build networks over time with this technology. Okay? And there's two general approaches seem to be happening. One is sort of an overlay model and one is a pure model. In the overlay model, what we're looking to do is just have IP routers at the edge of these networks, and inside you have a pure optical network. And we've been doing this for a long time. There's nothing new here. And the router becomes a client of the optical domain, okay? And the router can't necessarily see inside the optical domain. So the problems we see is that you have a little bit of stress when you do this on the protocol side. And this should look pretty familiar. You can think about IP routers on the outside and ATM network on the inside. Okay? And one of the problems with that architecture is that you had these routers on the outside, and in some cases you built networks where you had a full mesh of every single router had a PVC to every other router in the network. So the ATM devices had to scale to be able to have the number of PVCs to support that. But a bigger problem was that if you're a router and you have a connection to every other router, you've got an n-squared mesh in the network, and you've got this router has to keep up with all its IGP information, and that's a lot of stress. And the things like IGP mesh group, ISIS mesh groups were made to sort of try to solve some of that problem. Okay. So one question we have to ask is, you know, if we look at an overlay model, do we want to do that again? Does it make sense? Did we learn any lessons from overlay network models of the past, and can we now apply them, okay, to build next generation networks? In the pure model, we're looking at building a network infrastructure that has an integrated control plane. So the routers with the IP services can communicate with the optical devices, and they can share protocol information and control plane information, and the routers can understand what the infrastructure looks like at the optical layer, and they can make some intelligent decisions on how they're going to set up paths through that network. Another sort of approach to this is sort of mix the two, to be able to have, in some cases, a pure peer-based network, and in other cases, sort of a hybrid network, mixing the best of both worlds. And what we're going to look at having here is a uni interface now, in many cases, from the router world into the optical world. So a few things have been happening in standards bodies. One, in the OIF, in May 1998, so the standards body has started looking at developing a uni-based signaling model. So think about sort of like in the frame relay uni-based, in the frame relay uni or an ATM uni, user-to-network interface. And they were working with the IETF to sort of look at how do we leverage all the work we've done inside the MPLS working groups and taking now LDP, serial LDP, and RSVP and using that as a signaling protocol. Okay. Another and as well as what's happening in the IETF, as most of you know, is a lot of work has been done in a generalized MPLS working group. Okay? So taking this concept of multi-protocol lambda switching and generalizing it, and I have a few more slides on this a little bit later, to look at building this peer and hybrid model. Now alternatively, I'm ahead of myself here. So this is now sort of in the IETF, and this is sort of a new slide to me, so I'll apologize here, but I think a lot of this apparently is moving to the common control and measurement plane. And a lot of the original work was to extend OSPF and ISIS to make sure you can get all the attributes of the network that we've done already with MPLS and extending ISIS and OSPF, and now do that from a broader perspective. How do we now open this up to include all sorts of different circuit types and link types? Okay. And we're looking at the futures now with BGP, so how do we connect across autonomous systems, and how do we do carrier-of-carrier applications in the network? Okay. Okay. In the sense of building these unis from the OIF, what we're looking to do is run applications now so we can actually signal from the router across a uni and ask for services. But the the information that's kept inside of that optical domain will be hidden from us. Okay? And so this is a great way to bridge from today's networks, which don't really talk to the optical layer, the IP of the optical layer, to an interface now that will talk over a uni-standard, to eventually looking at a way to rebuild an integrated model of generalized multi-protocol label switching, that we can have all optical paths being created in the network, and we can have routers looking at those optical paths to see what is the most advantageous way to build something. Question?
Yes, and maybe having come like figuring out why the uni model is going to be better than the worse than the GMPLS model.
I don't think.
Sometimes, I think sometimes it's better because, as a router, I don't care what option to do. All I want is a path. The router is already.
So the question is, why is the uni model supposed to be better than GMPLS model, or the other way around? Worse.
From your thought, it seems that that's the way you're going.
That
uni model is in some sense worse off than the GMPLS model.
I would say that I guess what I'm trying to articulate is that I think the end point we'll get to is where we'll have an integrated model. We'll have optical devices talking to IP devices over generalized multi-protocol label switching. And so the IP devices can understand more of the topology information. I have a few slides coming up on this, but I think one of the reasons why is that if I'm routers on either end, and I can see an optical path through the middle that's already been set up, I'd like to be able to use that. As opposed to if I'm two routers from San Francisco to New York, and I have to call my optical group and say, can you set up a path, and that takes 4 weeks to set up, okay, through the network.
But that's exactly the problem that the uni is trying to solve, where the router signals the optical software. How the optical domain does it is particular, and at the other end, the cost goes up to the router. So why is it any better? Or worse?
I can't answer that. So, but I think it's a good point. Where has MPLS been? MPLS was sort of derived in its early stages to solve some of the traffic engineering problems. And we took a lot of the lessons we learned out of building ATM networks with traffic engineering and applied them now to the IP world with MPLS. How do we create a soft PVC in the IP world? How do we create an LSP? How do we create it from one endpoint to the other? And to be able to have the ability to reroute that LSP. We've been able to extend this technology now to offer next generation services like layer 2 and layer 3 MPLS VPNs. Okay? And so we can have a provider router in the middle, we can have provider PE routers, provider edge routers at the edge, we can have different virtual route forwarding tables and different forwarding tables sitting for different applications, so we can now connect off of one edge router, a blue VPN and a red VPN, across a common infrastructure to another blue or red VPN off that same network, but able to keep all the forwarding and routing information distinct and separate. Okay? And we have plenty of this technology up and running, both at Juniper and at Cisco and at some other vendors, and in interoperable standards. Okay. So what we want to do is try to take some of the technology that we've built in to MPLS so far, and we've leveraged off applications like ATM, and now generalize it into MPLS, so we can take this and build optical networks that talk to IP networks. Okay? So now what we want to be able to do is take TDM type infrastructure and physical port type switching and sort of build an integrated peer model. Some of the applications, some of the extensions that we're working on is the ability to now extend the IGP, both OSPF and ISIS, into the optical domain. So there's a common standards-based IGP that runs both at the router world inside the optical world as well. And you'll be able to set up different levels of a hierarchy. We'll take a look at why, because you have different layers from the physical fiber layer up to the DWDM layer, into the SONET layer, and et cetera. We're going to be able to control those different types of applications and be able to leverage the experience that we have inside of constraint-based routing, that some of the lessons we took out of the ATM world and brought into MPLS, and now extend that even further. So if we look at extending the IGP, what we want to sort of show is if we can now flood the information for all the different types of links that we're not used to having before. What we did is we went from the ATM role to IP is we took information like what type of link is it and how much bandwidth. Well, now we need to do that, but also extend the different types of link. Is it a packet link, which we're used to? Was it sort of cell ATM type of packet or an IP type of packet? But now we have different links, such as TDM and lambda links and fiber links, as well as a concept called a forwarding adjacency. And a forwarding adjacency, oops, I'm ahead of myself one. In addition, we need to take extensions that we haven't had so far, which is things like having new sub-TLVs, such as link type. And so what type of link is this? Is it a working link or a protection link? So if we see a working link go down and the protection link come up, we can now signal that through the IGP so everyone else understands that now we're on a different link as the primary link. Another type of sub-TLV we have is a shared link group, so a shared risk link group. So as we actually bundle links together, we might sort of take 3 links and actually bond them together. And if one of those links has a problem, we want to be able to send a message out via the IGP to everyone else in the network that says, look, this link actually has a problem, so you might not want to use it. Okay. A forwarding adjacency is a really interesting concept in that what we're trying to show is that if we set up a lambda LSP from one optical device, I mean it's an add-drop multiplexer in this sense, through different optical components, or in this case maybe it's a dense wave division multiplexing device to another end device. What we're able to do now is now take this forwarding adjacency and advertise it back into the IGP. Okay? As a forwarding adjacency at, let's say in this case, at a lambda level. And if it's a forwarding adjacency at a lambda level, then the routers can now see that there's a path from an optical device, let's say in San Francisco, to another device in New York. And now what they can do is say, well, since I already see that adjacency at the optical layer, all I need to do is signal now through that adjacency and say, I want to actually now set up my packet-based LSP through this adjacency. Some of the attributes that we need to look at is one of the traffic engineering metrics. I mean, how is this how is this LSP being engineered both at the optical layer, so keeping the traffic engineering information about that, as well as at the packet-based layer, okay, the LSP that actually tunnels through that. In addition, inside of GMPLS, what we're also doing is setting up different hierarchies. So we might have bundles that look at the fiber bundle. So as we have a conduit that runs from different city pairs, we can actually identify that and all the different fiber conduits that run through that, as well as the TDM network that runs across those, as well as any packets that run across, packet-based LSPs that run across that. So there's different hierarchies that we need to keep track of, and it's important because we can now, when we advertise in the IGP, we can identify what hierarchy this is part of, so the different devices who are concerned about the particular hierarchy can understand what layer to look at. And so an optical device will look at maybe a TDM type hierarchy, but it will ignore any of the packet-based information because it's not important to it at that point in time. All the lessons we learned inside of building constraint-based routing in MPLS devices, we can now apply in a general case to generalized multi-protocol label switching. So as we look at extending the IGP to take all this new information in, and we look at now trying to compute paths through the network based on those constraints, those traffic engineers' constraints, we can run this algorithm that sort of spits out the best explicit route through the network, both for a packet-based LSP as well as a TDM-based LSP, as well as sort of even for a fiber-connected type LSP. As long as we keep all the information that we need inside of the extended IGP and all the different components are looking at the applicable portion, we can now take this general type of constraint-based algorithm and now apply it across a variety of different domains. When we are using multi-protocol label switching in the packet-based world, we're used to having an explicit label. A label that sits inside the MPLS header, that's in this case a 20-bit label, in our current instantiation of MPLS. But now, as we look at bridging MPLS into the optical domain, we don't necessarily have an explicit label. What we have now at times is an implicit label that as you have to connect two different lambdas together, you might not necessarily, you have to actually signal this typically out of band. And so you might need to signal this through an out of band Ethernet or somewhere else. And so we need to actually define what those type of labels are inside of GMPLS and be able to signal them. Right now, LSPs are unidirectional inside of the current instantiation of MPLS, and there's a movement to now extend this to bidirectional LSPs, which we've seen in the ATM world for a long time. Soft PVCs and ATM are bidirectional. So there's a movement now to get bidirectional LSPs both at the packet-based world as well as in the optical world, and be able to extend RSVP so we can aggregate bundles of RSP message together in order to scale the protocols more effectively. So in the case of RSVP, we'll send a path message which includes basically a request to set up an LSP from one device in the network to another device, and we'll go from similar devices, meaning an IP router to an IP router or an optical device to an optical device, and we'll send a reservation message back saying that the resources are or are not available at that case, and if they are, and the message is received back at the original sender, then then the actual path has been set up in the network. One of the things we haven't needed today inside of MPLS is a link management protocol, because we assume that's being handled by a different layer, a layer that sits below us. But as we sort of connect optical devices, we need the ability to now understand what different types of links we're actually interfacing between and be able to manage those links. Let's skip this here. This sort of relates to the shared links group concept. So if we take now a bundle of lambdas, in this case, and we want to room them together, and maybe we want to take two different lambdas at OC48 and build a 5 gigabit channel between the two of them, we want to be able to have the ability to now group them together and understand that they're grouped together and advertise that into the IGP so we see them as one group. And that allows us to advertise that out to the IP router to say we have a larger channel and have the IP routers now be able to multiplex across those two channels, as well as to understand that they're actually a linked group together. And in case we have a failure, we can now recognize that both of those links are down. So some of the macro benefits we're looking for inside of GMPLS is to sort of create more open standards. The routing world has been used to having open standards. The optical world isn't necessarily used to having those open standards. And to create the open standards and to eliminate the need to have n-squared meshing problems, so that if we have just a pure overlay network and I have routers who want to talk to every other routers, we have to now create n squared or n times n minus 1 over 2 PVCs between all those, and that creates scaling problems at the protocol level for these. And if we can leverage a lot of the experience inside the traffic engineering world, we can hopefully build new next generation networks. So if we sort of bridge from the last century, the 20th century, and the 21st century, we're looking to now take a lot of that experience that we've seen inside of the overlay network and collapsing that to an integrated network from the IP and ATM world into the IP and optical world. Okay. And so now what we'll see actually, I think, is that routers are the largest consumers of bandwidth, or becoming some of the largest consumers of bandwidth, and have taken over that role from the voice equipment. And as that's happening, I think one of the key points here is we need to sort of architect these networks to leverage where the services are being created in the network and how we can actually integrate across an all-optical domain. So thank you. That was a little faster than I expected, and I do apologize since I am not the primary presenter, but I'm happy to take questions if I can answer them. It's been a while since I actually gave this presentation, so question?
I'll be first with it not having been able to follow most of that. It sounds like changing the network management aspect on the terminal may be much easier to go along than actually coming up with brand new protocols trying to replace something that for better or worse, actually works. I mean, Sonnet does work, and the overhead of Sonnet is trivial compared to ACM. And are you folks looking at maybe changing the actual management, the network management aspect, and provisioning of Sonnet, as opposed to trying to come up with brand new protocols replacing?
We're not necessarily trying to come up with ways to change the Sonnet provisioning, but one of the benefits of GMPLS is that if you can signal from a router through an optical domain to another router, and if you can only touch one router and that can talk to everything else along the path, then you don't have to have separate management systems talk to everything along the way. Okay? And I do agree with your point about Sonnet overhead. There's not that much overhead inside of a Sonnet path. And I actually think as these networks will evolve, we'll keep standard Sonnet framing because it works, and there's good operations and administration and maintenance inside of section line and path overhead that we use to keep those lines up and running.